pleased to introduce Professor Lyon here, and also want to welcome everyone back for our new season and new year of these seminar series, and look forward to another lineup that we have for you. And so here, Dr. Lyon is going to be presenting for us today a presentation on the Meso-scale Mhd simulations of the magnetosphere. And Dr. Lyon graduated with his PhD from University of Maryland, and his research interests include, of course, computational physics with magnetospheric applications, geophysics, and plasma and fusion physics as well. And in general, he's part of a team whose areas of investigation include evolution of the radiation belts, how the magnetic fields of the sun is, of course, interacting with the magnetic fields of the Earth, electrical currents in the ionosphere as well, and even the effects of cosmic rays, which have effects on radio communications as well near the poles. And all these initiatives are rooted in the mathematical codes developed by Professor Lyon as well. So with that, Dr. Lyon, take it away.
Okay, so this is actually, I'm actually going to present very little of my own work. I'm going to be hopping around with stuff that has been developed by the Center for Geospace Storms development team, which you can see listed there. There's a group at APL, some at NCAR, Rice, and our favorite Chinese person, Binzhen Zhang, who's at Hong Kong. So, quick outline. I want to talk about numerics at the Meso-scale. And one of the things that is important to talk about here is that the way that you solve the equations, the Mhd equations, is really important. That if you don't do it in a careful way, you're actually not going to be able to get at the Meso-scale, which we now believe is really important for the global structure of the magnetosphere and other systems. So I'm going to give you a little bit of history about what we did 30 years ago that's still useful, and how to get the most out of your simulation, our new code Gamera, a quick trip into the solar system, and show you some results from Venus and Jupiter. And then we'll talk about the Mage world, which is the thrust of the Center for Geospace Storms that Slava Merkin is running at APL. And I'm going to talk about some work that Karim Sarathia did with auroral beads, some particles that both Karim and I did, tracing particles in these high resolution simulations, and then some work that Kevin Fan has been doing on traveling atmospheric disturbances. So the first, as far as I know, Mhd simulation of the magnetosphere was something done by Steve Brecht and the rest of us at the Naval Research Laboratory when I was there, which was a calculation that was on 28 by 21 by 21 cells. And you can see in the picture there that it was really pretty crude. It used a code that had been developed by Klaus Hein. Actually, at NRL, they were doing bomb work. They were calculating things that went boom in the atmosphere, or above the atmosphere, in the ionosphere and above. And so this code was basically sort of 50s numerical, 50s, 60s numerical methods. Klaus had added some stuff that became the limiter. I'll get to that later, that we use in LFM and in Gamera. But it was spread shocks over 4 or 5 cells, which meant that you couldn't really tell the difference between the bow shock and the magnetopause, or the magnetosheet sort of disappeared. So in the early 80s here, and into the mid 80s, there was quite a bit of work going on what's known as shock capture and numerics. And so we decided that it was worth writing a code that would try to use the best practices that were available at the time. And so we had major design decisions. One is that we would use a high order total variation diminishing. You'll hear TVD quite a bit, and I'll get to what that is, transport algorithm. We wanted to use a finite volume non-orthogonal grid so that we could pack cells where we needed them. And we also wanted to make sure that we had the divergence of B equal to 0 to round off. And so the other plot up there is the velocity field from Fetter and Lyon paper in 1995. And basically, I tried to get something that was closer to when we actually developed a picture for when we were actually closer to when we developed the code, but this is as close as I could come. And you can see that A, we're using a much different grid, and B, the resolution seems to be quite a bit better. Okay, now, total variation diminishing is basically means that if you have a solution that shouldn't get a new extremum, the algorithm will make sure that it doesn't do that. There's an issue that you run into, and that is that if you try to write a numerical scheme where you have an accurate, in terms of a Taylor series solution, shocks will cause it to blow up. And that's not good, because what happens in both hydrodynamics and in MHD is that a shock type situation is self-steepening, which means that it basically sends energy to shorter and shorter wavelengths, and when you get to when that energy gets to the grid scale, bad things happen. You can solve this by using a very diffusive scheme, basically what's known as first order. Unfortunately, it doesn't show much structure, and up at top you can see a highly resolved solution for this problem, which is basically a Riemann shock tube problem. It's a change in magnetic field and density across in the center of the grid, and then that propagates. Now, if I tried using a centered scheme, I get this, which if you can see at top, when it finally quits, it's actually has an imaginary time step, so that's not very useful. So how do we fix this? What TVD schemes try to do is to mix the accurate and diffusive solutions. And they do this by using a nonlinear switch. It's called a limiter. And the switch tries to figure out when you need to switch from using an accurate solution to one that's diffusive enough to keep things under control. So the way that this is usually done is that first you reconstruct the solution. And off to the right there, I have a fairly narrow Gaussian with the computational cell structure indicated. And it also shows how you might reconstruct the solution, that is, try to determine what the actual solution is at various points on the grid. So the magenta points are what you would get if you used an upwind donor cell, which basically means you look to the cell to your, in this particular case, have things moving to the right, so you look to the left to get the upwind value. And then you can also try doing a second order, which is basically a linear interpolation between points, between cell centers, or a fourth order scheme. And below, you can see the error that you get between the real solution and what your numerical method is giving you. And you can see that the numerical error goes down rather rapidly as you go to higher and higher orders. Now, how does the limiter work? Well, it looks in the neighborhood and decides whether you need to do any change. Below here, we have the limiter that's used in LFM and Gamera, and what you should think of is that the whole distribution moves to the right a certain amount, which is basically the brownish area there from row I minus 1 into row I. And so that's flux coming in, and then there's flux going out, which is the green amount over there, which is what the limiter says is the minimum allowable amount that you can get out, that you can leave. And the way you determine this is that if you take the brown minus the green has to be less than that purple area in there. So I know I'm not explaining that very well, but but you can see that there's an algorithm that allows you to decide that that point row I is never going to get any bigger than row I minus 1. There are other ways of doing this. One common method is a slope limiter, which basically here I've shown the slope between row I minus 1 and row I plus 1, row I plus 1. And if you apply that slope to the row I, you get a limit on how high or low the interface value, that is at I plus a half, can be. And there are various ways that you do this. They're all, last time I looked, there were probably 40 or 50 different ways of doing this. So if you do this, you actually end up with something pretty reasonable. This is a second order, numerically a second order scheme with TBD limiters. Up above is something over 2,000 cells, which is the actual solution, sort of. There are a couple of artifacts here and here, but other than that, you can see that it's just there's a rarefaction fan, a shock, constant pressure, contact surface, another shock, and then a rarefaction fan over there. So if I use what's known as a super B limiter, which is a slope limiter with very high, which is what you would call aggressive, that is, it allows the maximum amount of slope, you can see that you're getting there, but that the solution has some wiggles and that you'd prefer not to have. If you use a somewhat less aggressive limiter, this is the Van Leer limiter, you can see that now things are very much smoother, but not quite as sharp. So one thing that is important with regard to LFM and Gamera is that if you use high order interpolation, that is fourth order, eighth order, whatever, you can get away with using much more aggressive limiting, because the solution, that is the Taylor series, is able to carry, that you're mimicking, is able to accurately represent much steeper structures. So one way of looking at this is to talk about the linear advection test, which is to move various shapes at constant speed and see how good the solution is. One nice thing about this is that when you do a square wave, which is the square wave, which is that second from the left, you can actually, it's actually pretty close to looking as though it's convolved with a Gaussian. So you can use that model equation up there in the upper right, which gives you a diffusion coefficient, an effective diffusion coefficient for your scheme. And so if you do that, you can see that as you go to higher order, things get much better. The width actually goes down quite substantially, and you can get an effective Reynolds number for the advection. A first order scheme has something that's known as a cell Reynolds number, which basically means that you have a certain number of cells, and so you can't have diffusion has got to happen on the cell size. And so if you have 100 cells in one direction, the cell Reynolds number is basically 100 or thereabouts. A relatively small number, even for the large calculations that we're able to do these days. The cell Reynolds number is small enough that most of the structure that you would like to see, because the magnetosphere and virtually every space system has a very high Reynolds number, almost dissipationless in that sense. And that leads to different phenomena than you would get with a low Reynolds number. In any event, you can see that as you go to higher order, you're able to do a much, much better job of mimicking the structures that are advected. And on the lower left and lower right there, you can see the effective Reynolds number plotted as a function of interpolation order. And so 0 is effectively 1. That's your cell Reynolds number. And by the time you get up to fourth order, you're beginning to crack close to 100 times better Reynolds number for advection, which means you can get into the range where the flow that you model is highly turbulent. One thing that we thought was important was the question of the divergence of B. The numerical treatment it's one of these issues. It's kind of like Emacs versus Vim. You have people on both sides, and we, I think, are on the side of wanting the divergence of B to be equal to 0. The issue arises because when you start using these TVD schemes, typically you can see in the little volume down there of the hexahedron, that the nominal hexahedron. When you start using a cell-centered scheme, then you have fluxes, that is numerical transport going out of different faces, and the nonlinear switches are going to operate on those differently in general, which means that the nice, neat mathematical cancellation of div and curl doesn't work anymore. So you start to get divergence of B showing up. Well, the big problem with that is that you get then a a term which is B times div B in the Maxwell stresses, which is field aligned, which is really bad since magnetic stresses are only supposed to be perpendicular to the field. To solve this, people add extra terms to the equation. So you have a term in the Maxwell stress, which is minus B div B. So you add a term, which is, as a source term, B div B. So in theory, it all cancels out. Then you have to do something to keep track of div B, hopefully to take it down to 0. The simplest thing to do is just have an advection equation. This was what people did initially, and that doesn't work very well if you have a stagnation point. And various other techniques have been developed to do this. It's not clear to me, and that it's worth taking the chance that you're going to run into trouble. For one thing, if you have non-zero div B, your helicity is no longer a constant of the motion. The alternative which we use in LFM and in Gamera is the E grid. And on the lower right grid there, basic picture, you can see how things line up. Phi is the magnetic flux going through a face, and E is the electric field. And if you apply a nonlinear switch to one of these corner E's, then it affects it affects one face one way and the other face the other way. So flux is basically just transported across that edge. And this is the basis of what's known as constrained transport. And it works quite well. One thing is that you can show that there's a construction. The simplest one is just a linear interpolation of the phase flux from one face to the other, that not only is div B in this global sense, but is div B everywhere within the cell. So that said, then we have Gamera. Gamera is an improved reimagining of LFM, maintaining these key elements. It's higher order differencing and transport, grid flexibility, and maintenance of div B equals 0. It's been extensively tested, and we feel that it's a very, it's a very general and very agile way of doing the Mhd solutions. There are many improvements relative to LFM. One is software modularity. It's now relatively easy to plug in various things, either a new grid or a new way of solving the transport. It also has an open MPI structure, hybrid structure, which means that you can either use threading on a given processor, or you can use MPI, or both. We actually use both most of the times because it cuts down on the amount of MPI communication. There's enhanced grid flexibility, 2D and 3D non-orthogonal grids you just get from input files, more accurate metric calculations. Kareem, who is responsible for most of the writing of Gamera, actually has implemented 12th order metric calculations for grids that have analytic solutions. And the code is much faster. When we started building the code back in the 80s, the fastest machine was a few megaflops, 1 million operations per second, and was vector to vector. And so in order to make it efficient for that, you wrote the code in a certain way. It's much different now, and Kareem has done a good job in making it fast. It's also set up in a way that the structure is suited so you can use coprocessors. The most common one these days is a GPU. The axis singularity, since we use a quasi-spherical grid, we have a singularity along the axis, which we average on, and that's been much improved. If you're interested, you can go to that website there, click on the models, and then, oops, there it goes again. Okay, spell check gets me. Meso-scale always ends up being mesh scale. In any event, you can click on models, then click on Gamera, and below are the papers that will tell you in more detail than you would ever want how the algorithms work. And there is Gamera, and he's going to show us what he can do. Okay, so here's a test problem that we did in Gamera, and it shows a couple of things. This is a slotted cylinder test. It does advection of the density distribution around the center of rotation, shows the difference between high and low order transport, and there are 4 different grids to show that actually Gamera, which is grid agnostic MHD for extended research activities, something like that. In any event, so this shows the way the problem is set up. You just rotate about the center. This rotation you can see is going through Cartesian grid, a distorted grid, a regular polar grid, and just a warp grid. Oops, let me go back. And you can see here the difference in resolution between using a 2nd order scheme and one the 7th order, which is actually an 8th order scheme that hasn't a 7th order, or it's an 8th order scheme with a slight 8th order diffusion, but effectively 7th order. So, just for comparison, if you do the same problem, the same problem, 24 by 1024 by 1024 2nd order with a very diffusive limiter, you get one solution. And if you do the 7th order PDM, you get pretty much the same solution. And that's a factor of 8 in resolution, which if you translate it to a 3D explicit code, that would be about 4,000 times, a factor of 4,000 in computer time. And just for grins, over on the top right, I have the top 500 supercomputers performance over time. 4,000, a factor of 4,000 on that plot is the green bars. And the arrow shows how long you'd have to wait to go from using our high order scheme to getting the same answer using a low order scheme. And one other nice feature about using a higher order scheme is that the rate at which this numerically advected square wave gets broader, goes down, so that you actually end up over a long period of time actually being better. So it actually turns out that by the fourth and eighth, they're pretty close, and they're both get bigger, get broader by the fourth root, the fourth root of the time. So it's a very slow, this is something we noticed early on. Okay, so some preliminary results with for Venus with Gamera. It shows the flexibility of the grid. That is the size of the grid in the near Venus is in the radial direction 5 kilometers, and it's more like 70 kilometers azimuthally or in the polar direction. And Gamera has no trouble handling that, which is a very large aspect ratio. So this particular thing is a multi-fluid calculation. The LFM since early 2000s, I guess, has been multi-fluid. And Gamera has also got multi-fluid capability. And it's got chemistry for O+, O2+, CO2+, and solar wind interaction. So this is 2 separate calculations, and I'm showing these basically to show the difference between, once again, low order calculation and a high order calculation. And you can see that all of the structure that you get in the high order calculation, which is the one at the top, and the structure that you see behind the planet is actually reminiscent of this sketch here on the top right. One of the really nice calculations is of Jupiter that Bin Zhang has been doing. Basically, once again, a multi-fluid calculation, and you can see that loading up the water type molecules close to Jupiter and letting them run, you can see a couple of things. One is the very large, really tailored rolls that you get pretty much on one side. And then also there's instability, the interchange instability driven by the rotation close to the planet. And it gives you a rather strange topology for the interaction with the solar wind, where the actual reconnection line is off to the flank, off to the dusk flank. And once stuff becomes reconnected, in contradistinction to the Earth, where the solar wind is strong enough to pull it across the top of the polar cap, the Jupiter rotation wins every time. So this green area here, the open IMF, actually ends up being a band in the polar cap. And this region in here is actually, across the top of the polar cap, is actually connected to the interior of Jupiter, which leads to the difference in the aurora, the auroral oval in Jupiter, where in the Earth, you've got a dark polar region, but in Jupiter, you've got a aurora showing up in the middle, in the top of the polar cap. But there is a dark region here, which is corresponds to, oops, well, all right, to the open region. Okay, so moving now to the major thrust of our efforts, which is the Center for Geospace Storms. What we're most dealing with here is the Mhd model, which you've seen this sort of thing before from SWMF and also from CISM back in the day, of a whole set of coupled models together. And here we're trying to go from the actual troposphere out to the solar wind through the use of WACM-X, which is the community whole atmosphere model, and various other things, a ring current model, an ionospheric model, polar wind outflow, and particle tracing, and also the SAMI ionospheric model. Okay, so first up, we're going to do just the simplest stuff, which is the remix and Gamera, which is basically the same thing as the LFM had been for a long time, except better. And here up at the top is a the highest resolution simulation that's been done. This is the hex simulation. And the left-hand plot is in the equatorial plane and shows essentially the magnetic field with the dipole taken off, pressure on the right-hand side in the meridional plane, and the solar and the polar caps, field-aligned currents and potential are shown top in the insets. And you can see the huge amount of structure that you get. One important thing that we'll get to in a second is about here, where you can see these little beads forming on the, up in here. And those are actually, we think, are auroral beads, the formation of auroral beads. Below, once again, I'm going to show you the difference between the high resolution simulations with a high order numerics and a low order scheme. And you can see that there is no Meso-scale. If you go to something basically a second order scheme with a fairly unaggressive limiter, you get basically no structure, no Meso-scale structure, as opposed to the higher order structure. Okay, so let me show you in the growth phase, the near-Earth plasma sheet becomes interchange unstable, and I'll show this movie over the short period. Here's the southward turning, and we're starting in the growth phase, and you can see these bubbles, these fingers forming. And if you map those down to the ionosphere, you get this sort of a structure using the upward field-aligned currents as indicator of the aurora. And this is a similar sort of all-sky camera from the Themis array. This is work that Kareem did and is appeared in GRL back in last year. So here's an inset that shows these bubbles a little more carefully, a little more closely, and you can see that the movie shows here the field-aligned, the flux tube entropy. If the flux tube entropy is reversed, that is, it's low, close to the Earth, and gets higher as you go away. But if you get a reversal, it becomes interchange unstable, and you can, get these fingers. And this upper plot shows the field-aligned currents in the ionosphere, and you can see these little fingers of field-aligned current forming, which give rise to the bubbles. Okay, next step, Gamera chimp, particle tracing in MHD fields. These two plots are of releasing some particles of relatively low energy on this arc here, and seeing what happens as you let the MHD fields move it around. On one side, you have a relatively low resolution plot. You can sort of see from the outside here that these blobs or BDFs are relatively broad and on this side and narrower on this side. And it leads to a rather large difference in the solution, or the final state. In the final state, from this calculation, the lower resolution case has got stuff that is basically outside of geosynchronous, whereas, I keep doing that, I'm sorry. Whereas the higher resolution actually brings stuff in closer, and you can see the time averaged mass flux for these particles over here on the left. And SR is the lower resolution, and SR2 is a doubling of the resolution. And actually the mass flux is actually more closer to the Earth with the higher resolution. So it's important to have a high resolution solution for this stuff. Now, this is a solution with a very similar, but this time it's cusp outflow of stuff moving at roughly, oxygen moving at roughly 20 kilometers per second outward. And what you can see is that on the left-hand side is a same type plot with the magnetic field shown with many bursty bulk flows. On the right-hand side is the cloud of particles that was released at the same time, at the same interval. And it's color-coded by energy, and you can see these streaks of higher energy particles, and these are actually being picked up by these BDFs and accelerated. And so the Meso-scale, in this particular case, actually is important for where oxygen ends up. It turns out that you can quite rapidly put oxygen into the ring current by these BDFs picking it up. One important thing is that we need to worry about is grid convergence, which is do you get a different result if you increase your grid resolution? And it turns out for this particular problem, it looks as though we're starting to converge. The blue points are what you get at a given time with using a quad calculation, which is 4 times coarser than the yellow hex calculation and 2 times coarser than the red oct. And the blue is clearly very different from the red and yellow, but it looks as though we're starting to get comparable results with the oct and hex resolutions. Okay. So this is the mini Mhd, which is being used now, is sort of our go-to solution, our go-to coupled set of models right now, which has the Gamera Mhd, the Remix, ionospheric electrodynamics. Ultimately, we're going to couple to Wacom X for the ionosphere and lower atmosphere. But currently we're using TiGCM, and the ring current is coming from RCM. And just for comparison, this is where we are with regard to this mini Mhd. The top left shows Gamera with TiGCM coupled in, but no RCM. Below is mini Mhd, which has the RCM coupled in, and you can see that the region 2 currents, that is the blue at low latitude on the left and the red on the dawn side, are very much stronger with the addition of the RCM, and the overall resolution of the solution looks very much better. This particular interval was studied by Ampere, and you can see the A, next to the A there is the Ampere field-aligned currents. And it looks as though we're doing a reasonably good job with that, with the RCM in there. The Weimer model is, of course, spread out because it's an empirical averaged model. And the old LFM, which is relatively low resolution, has sort of some of the same features, but really needs a lot of work. So overall, I think we're very pleased with how mini Mhd is behaving. One of the things that I'd like to just touch on is work that Kevin Pham has been doing with traveling atmospheric and ionospheric disturbances. And these are waves that can travel around the globe and driven by Joule heating in the polar ionosphere. If you use the Weimer model, which we saw before, to drive TiGCM, and you ask how do the neutral densities that satellites see with regard to what TiGCM would give you, you can see that the overall comparison is not terrific. Not too surprisingly, because the empirical models tend to give you the gross features, but not any of the detailed Meso-scale stuff. For comparison, well, the movie shows the TiGCM solution for the neutral atmosphere driven by mini-MAGE. And crossing it are the satellites of Grace and Champ. Grace in blue, red in Champ. And down below is traced the model results for each of these satellites. And you can see that the overall comparison is now very much better, and it's clear that these waves are being produced on the mesoscale in the ionosphere, and when there's a big peak, it's the satellites are passing through something that has just been either developed or has been propagating down to lower latitude. And the comparison is really quite good. And over to the right here, you can see that the reason is fairly simple to see. That is that the Joule heating from mini-MAGE is now very much structured and localized. And so you get certainly a different, and it looks like a much better calculation of what is actually driving these waves. So, I don't really have many conclusions other than things are working well, and we now can really look at how mesoscale phenomena operate to affect the global scale. And that's it. Thank you.
Excellent. Thank you very much, John. We really appreciated this presentation. And you've actually got quite a bit of feedback here in the chat that I've been monitoring. I do want to mention, in case people have to jump off just before that, next week is a holiday. So I hope everyone enjoys that for Martin Luther King Day. But we will resume on the 25th with a presentation by Rick Chappell. But in the meantime, now some questions just in the order in which they came in here. It looks like on some of the interest slides, another John had asked, could you clarify what you mean by the imaginary time step and how you ended up with that? I suspect maybe there was a numerical thing that happened, but he was curious about that.
It's the imaginary times. For some reason, that was a MATLAB calculation. And for some reason, MATLAB decided that when it got the square root of a minus number, it would just keep on going. So,
sure.
Most likely the pressure went negative, or the pressure density went negative, and all of a sudden, most of the codes will die before that. But
sure. Yeah, I figured it was something along those lines. And next we had Eric was curious about the linear advection test, and he wondered if the effective Reynolds number had an asymptotic limit. I think you had showed several cases there, but did it converge, I guess?
Well, it's hard to say exactly, because you have the nonlinear switches involved, and they're what's actually causing it. But the numerical tests that we've done basically do seem to be going to a limit. I've actually done pseudospectral on, I think, 200, pseudospectral on a 200-point grid, and it's a little bit better, but basically, if you sort of drew an asymptote to that one graph, it would be close.
Sure. Okay, great. Thank you. And actually, Kareem has been doing a good job of replying to many of the questions already. So I'm just jumping to a couple of the larger ones here. Jason had asked, in case you'd like to comment, he says, what do you think causes the reversal of the entropy gradient, which allowed for those simulation beads to form? And Slava had commented there as well, but I just want to give that question to you too and see if you have any thoughts.
Well, I think it's probably there are two issues and two things going on, and I don't know which is more important. That is that the convection actually, Antonio Sato has brought this up. Convection actually gets sort of pulled around initially on the night side, and that could have an effect. The other effect is, of course, that when you start reconnecting, you start pressing down on the field so that you're changing the configuration, and I don't know which is which. If Kareem wants to chime in on this, I'd be happy to have him do it.
Sure. Yeah, actually, in some of the other comments here, Slava had mentioned too that there's also sort of a BZ minimum that can form on the edge due to magnetic flux evacuation on the day side.
Yeah.
So there's some other comments there in the chat that people can read. So and also, yeah, Slava had said the beads are the only upward current part of the full wavelength. So. All right, and then jumping ahead here, so Natalia had asked an interesting question about numerical resistivity, and I believe Kareem had answered here, but I'll just read that as well. Natalia asks, if the numerical resistivity is too large, the solution is too diffusive, but if the numerical resistivity is too low, there is no convergence of the solution and the plasmoid turbulence can set in. So she was saying the realistic value is likely somewhere in between and controlled by kinetic effects. How does Gamera check and control the needed resistivity value? And Kareem had commented, the numerical resistivity being too low is not something we'd likely need to worry about for the typical Reynolds numbers in these systems. But I didn't know if you had any additional comments to that reply.
Yeah, I would say that what we one of the reasons we like a high order interpolation methods is that what we find is typically if you have a, let's say something like a Harris sheet that you're not forcing to reconnect, it will pretty much sit there. That there is not enough numerical resistivity to force the solution. The other thing is that the way that typically Gamera and LFM reconnect is through averaging error. That is, if you force oppositely directed fluxes into one cell, then it, some of it annihilates, and so you get reconnection. What we find is that the number that we get, no matter the resolution, if the reconnection rate basically ends up being about 1/10 of the Alfvén speed, which is the canonical value, independent of our grid size.
Great. Okay, well, thank you very much. I think that covers most of the questions here, and there could even be some additional discussion later if folks, of course, would like to follow up. But that does bring us to the top of the hour. So with that, yeah, thank you again, Professor Lyon, for this excellent presentation and generated some great discussion and good questions in the chat. So, so with that, we'll hope to see everyone again on the 25th with the next presentation. So thank you, everyone.